Now, I've talked to you a lot about Einstein's successes, and you'll have heard about gravitational waves as another success. But gravitational waves were almost a big failure for Albert Einstein, because when he first wrote a paper about them, he predicted that they could not exist at all. And he sent his paper off to a scientific journal in order to get it published. And then someone else looked at his paper and they worked through it and they checked his maths, and his maths was wrong. And so because of this wrong maths, he had predicted exactly the opposite of what he would later predict and what we've now just measured. He had a bit of form with having trouble occasionally with his general relativity, because another thing that it did is that it gave an equation basically predicting how the size of the universe would change. And when he looked at all of the matter, all of the energy in the universe, the equation basically said that all of that would have a gravitational pull inwards, which means that the universe, even if it started out expanding, would be slowing down and eventually would stop expanding and start contracting back in. And Einstein did not like this, so he fudged it. He actually put in an extra term, which he called the cosmological constant, which was he basically put in there so that he could have a situation where the universe was just going to stay and be basically the same size forever and wouldn't change. And then some measurements from telescopes looking at distant stars and how the light from them was changed by the Doppler effect of them moving towards or away from us, showed that all of the stars in distant galaxies were all moving away from us, so the universe was expanding. And so he went on and said that the cosmological constant was his greatest mistake. But there's another twist to the tale still, because it turns out that the universe is not only expanding, but how fast it's expanding, it's accelerating, it's getting even faster. There is some sort of term that needs to be added to the equation to account for this, to actually cause this. And physicists don't really know what it is, so we call it dark energy. And we do have dark energy in some the energy of the vacuum, one possible explanation for this in some of our other theories. But the problem is, if you look at the size of the effects in these two different theories, one looking at the universe, one looking at particle physics, you end up with something which is different by a factor of 10 to the power of 120. That's 1 with 120 zeros after it. In base 10. It's a lot bigger looking in binary. Well, that's massive, and we still don't know where that is. But we do know that that mostly he was right. And I want to just kind of give you a little bit of a taste of just a little experiment you can do in your head. We call it a thought experiment, to think about why gravity must affect light. So who here has heard of the equation E equals mc squared? Yeah, basically all of you. Who here knows what E and C mean in that equation? Yeah?
E is energy equals mass or velocity.
Mass per what?
Velocity.
Yes, C is not just the velocity, it's the speed of light in a vacuum, which is huge. And when you square it, it gets even bigger. So what I'm saying is that you can convert a very small amount of mass into a large amount of energy. And this is what happens in nuclear fusion in the sun and nuclear fission in nuclear reactors. So if we take that, we know we can swap between mass and energy. And I'd like you all to imagine a big tower built somewhere on Earth. And so you stand on the top of the tower with your mass and you drop it. What happens to the mass? It breaks. And quite possibly when it hits the ground, yes. But what does it do to get down to the ground? Flies in the air. As it's going down, does it get quicker or slower? Yeah, as it's going down in gravity, it'll be accelerated by gravity, it'll get quicker. And so we like to call that gaining kinetic energy. So now it's got energy not just because of its mass, but also because of its movement. And when it reaches the bottom, I'd like you to imagine a nice black box. We don't know what goes on inside it, but what we do know is it changes all of the energy both the kinetic energy and the energy due to the mass of that back into light. And it sends that light back up the tower. It shines light back up to the top of the tower, where at the top we've got another box which takes all of that energy in and turns it back into mass. So if the light doesn't change on its way up, we have a mass at the top, we drop it and it gains kinetic energy when it goes down. So when it hits the box at the bottom, it has got more energy from that is converted into light than the mass had at the top. And if we just send the light back up and it keeps all of that energy, hey presto, we've made some energy at the top. We've now got a heavier mass at the top. We can drop that down again, the light will come back up, and we'll have more energy again. We don't have infinite energy, which is a shame, because that just doesn't work. All energy cannot be created or destroyed. It can only be transferred between different types. And so that means as we're going up, something must be happening to the light. So that it's a form of energy that we basically can't do anything with at the top. And the way that this manifests is that light will actually change in colour when it's going into or leaving a gravitational field, well, like the gravity of the Earth. And there's something even weirder there, because when I was talking at the start about the photoelectric effect, each lump of light that corresponded to a different colour, and there's actually an equation for linking the energy of the particle of light to the frequency of light, the number of waves per second, and that's E equals hf. So if the energy changes, the frequency of the light has to change as well. And so we've got something really weird. We've got someone at the bottom of the tower and the top of the tower, each seeing the same light, but disagreeing on how long it takes for the light to do one whole wave. And so we can work out from that very, very slightly, the effect is tiny around the Earth. The two people, one on the top of the tower and one on the bottom, will disagree about how fast time is flowing. And so this does actually mean that your head and your feet are aging at very slightly different speeds. But it's so tiny, you would never notice that. You'd only notice that if you had to deal with something which had to be accurate to within billionths of a second or more. And it was coming from a signal which was a little bit further away from the Earth, perhaps something on a satellite. Because GPS satellites are sat far enough away. And for those of you who don't know, GPS works by basically taking signals from lots of these different GPS satellites. And all they're doing is saying what time they think it is. And all those different signals are being received by your GPS receiver, your phone, and it's converting the difference in the times from all of these different satellites into a position. It's just basically triangulating from several different things. But we needed to actually tweak the clocks on those satellites before we put them in orbit. Because when they're in orbit, time is flowing differently for the satellites in orbit than it is down here on Earth. So Einstein's theory of general relativity, gravitational waves are new, but Einstein's theory of general relativity has been having an influence in our lives for quite a bit longer than that through GPS. Thank you very much.